All right, welcome everybody. This week we are going over NMR. NMR is our third spectroscopy we are going to learn for this unit, as well as organic chemistry. The first two, just a quick brief on what we went over in the past 2 weeks. We went over IR, which helps identify functional groups. Last week we went over mass spec, which helps us identify fragments as well as counting the weights of different structures, stability of carbocations, and getting identifying patterns of heteroatoms. This week we will learn about NMR, which stands for nuclear magnetic resonance. And the main purpose of NMR is to identify, well, in NMR there are two types. There are HNMR as well as CNMR. And like I was saying, the main purpose of NMR, whether that's HNMR or CNMR, and if HNMR of course stands for hydrogen, as well as CNMR stands for carbon. The purpose is to see how each of those hydrogens or carbons are structured in the overall structure. And that will make more sense once I explain all the details of NMR. So to understand how NMR works and to solve a NMR problem, there are several different factors you have to take into account, at least 7. Okay, there are not in any order of importance by any chance or a checklist. These are just a list of items you have to learn to understand how NMR works. So first up, we have something called unique signals. Okay, and that is exactly what it sounds like. Unique signals are different hydrogens or different carbons, and to keep it simple, we're just going to talk about HNMR. Okay, so on a particular structure, you will have several different hydrogens. Some are going to be different or unique, and some are going to be similar. Here is an example. Okay, so I have butane, which is a 5-member carbon chain, and I have to identify hydrogens. Okay, so there are hydrogens here. Actually, we're also going to zoom in. So like I was saying, the goal is to find all the hydrogens. So there's 3 right there, 2 right there, 2 right there, 2 right there, and 3 right here. Okay, now we want to see if there are any lines of symmetry, because if there are, that means we have similar atoms who emit the same resonance, the nuclear magnetic resonance that we go over. Okay, so as you can see, there is line of symmetry down the middle, which means that we're going to number these, so, or letter these. So let's say that's a group of A, group of A. So both A groups are on opposite sides of this dotted line, and both of these methyl groups, hydrogens, are going to have the same unique resonance. And I use the term resonance in a different manner than what you are usually used to, which is, a charge resonating with the bond. Think of this as a different kind of resonance. Okay, so like I was saying, this A set of hydrogens are exactly as this A set of hydrogens. Next, we have B right here, and B right there. And then, of course, in the middle, we have C. Okay, so on a butane chain, we have only 3 unique hydrogens, or three unique types of hydrogens. Okay, and of course, these types also mean signals. So this signal is going to be the same as this signal. These two are going to be similar, and of course, because this is in the middle, it only has one unique one right here. Okay, so this structure would have 3 unique signals. Okay, and that is important because when we get to the graph, you'll understand abundance as well as the numbers above the peaks, but more on that later. So on to our next important item for NMR is something called multiplicity. Okay? And it has a formula as well. So multiplicity is how when you get your NMR graph and you have several different peaks, multiplicity is how you can tell what neighboring hydrogens are nearby. Okay, and that is exactly what the N stands for here. Okay, N equals neighboring hydrogens. Okay, and then however many neighboring hydrogens there are, you have to add +1 to it. Okay, for example, if we are looking at a set of signals or signal, so the signal of the A hydrogens is nearby the B set of hydrogens, and B has 2 hydrogens neighboring A. Okay, so we would add 2 for our N +1, and we'll get our multiplicity of 3. That A is so A's multiplicity would be 3, and B's multiplicity would be 4. B's multiplicity. So ignoring the mirror, because this would technically emit twice because there's symmetry. But we'll give a better example using multiplicity. But before that, I want to address the nomenclature of each multiplicity. Again, like I said, so NMR, IR peaks were coming from top to bottom. NMR peaks will go the opposite way, bottom to top. There's only like spikes. There's no like broad or anything like that, like in IR. So this is a singlet. This is a doublet. This is a triplet. This is a quartet. And anything after 4, so 5 and above, is simply known as multiplet. And on the graph, it just kind of looks like a bunch of lines. Okay. Sometimes it's worth noting the exact number of multiplicities. Sometimes it really does not matter because you won't need it to solve the entire problem. Okay, so to review, this is a singlet. That's rather big. Okay. This is a doublet. triplet, quartet, and multiplet. Again, this is known as multiplicity, and it has a formula, n+1. It should be fairly simple, so please don't forget this formula when calculating multiplicity. Okay, and we're going to apply multiplicity to this structure. Okay, so the first step again is to calculate the unique signals. So I'm going to quickly go ahead and do that. This time I'll do it in purple. So, and again, the first step is to find lines of symmetry. On this particular structure, I do not see any lines of symmetry, so I will have to assume all hydrogens are going to be unique. So I'm going to label them by letters. So A, B, C, D, E. Okay, so we have 5 unique set of hydrogens, and now we're going to take a look at each of the multiplicities. Okay, so when we're looking at A is only neighboring, or A's neighbors is only B, because C, D, and E are too far away. Okay, neighboring hydrogens have to be exactly 1 carbon away. 1 carbon away, or 3 bonds from the hydrogen. So hydrogen to the carbon, and then carbon to carbon, and then carbon to hydrogen. That is exactly 3 bonds. Okay? So, like I said, A's neighbor is B. B has 2 hydrogens because this is a CH2, because it's like an inside. So A's multiplicity would be a triplet. Okay, and I will write that in a different color. So A is triplet. So B's neighbor is A. So they're neighboring each other. There's no hydrogens here, so there's no neighboring hydrogens here. So we can't really count anything right here. So A has 3 hydrogens, so 3 plus 1 is 4. B's multiplicity is a quartet. And C is similar to B, where it's only neighboring 1 other set, but this time D only has 2 hydrogens because B, C, and D are CH2s, A and E are CH3s because they're methyl groups and they're on the outside. So C's multiplicity would be 2 plus 1, which is a triplet. And D is where it gets slightly complicated because now it's neighboring not only C, but it's also neighboring E. So it's neighboring on both sides. So we have to add the total number of hydrogens it's neighboring. So it's neighboring 2 from C and 3 from E. So together that makes 5, and then 5 plus 1 equals 6. So D's multiplicity comes out to a well, it's technically like a sextet, but we will just call that a multiplet because anything after 5 or 5 and above, we just note it as multiplet. And then E should be easy. E is just neighboring D, and D has 2, so it's going to be a triplet. Okay, so that is how you find multiplicity of to a set of hydrogens. And of course, you have to find each unique signal. to do this properly. All right. So the next item is location in terms of ppm. Okay, so ppm is the unit of measurement we use on our graph. That is on the y-axis, sorry, the x-axis. And just like IR, where there was a fingerprint region that we kind of ignored, there is a similar benchmark on NMR, okay? But instead of ignoring it, well, we do kind of ignore it, but there's something called TMS, okay? And that TMS value will always be 0 ppm, okay? So this is, again, a benchmark that we use to compare the rest of these signals, okay? If we are going to the left of the graph, it is called downfield, as well as, or rather, and if we go to the right, it's called upfield, okay? Now, if downfield and upfield, those are terms you will mainly use or hear, but sometimes your professor may also say deshielded or shielded. So deshielded is going to be associated with downfield, and upfield will be associated with shielded, okay? And the shielded and deshielding comes from electron withdrawing atoms and how their effect on, as electrons. Okay. So like you had to learn IR values for certain functional groups, for example, like 2200, before or after is where like the triple bonds are, and mass spec you had to learn the heteroatom like patterns, signals, numbers. That's the same for NMR. There will be functional groups here, and you have to know which hydrogens belong to which functional groups, okay? And that will all make sense once we're done with this lesson and I go over a proper example. But for now, understand that this is one of the main tools that we also use in addition to multiplicity and unique signals. Next up, we have chemical shifts for number 4, and that is associated with shielding and deshielding. Okay, so understand that even though there are set parameters for each of these functional groups that contain hydrogens, there may be other functional groups near those hydrogens or near other functional groups that push it either upfield or downfield because of the effect they have on the neighboring functional groups. So nothing really you can get from chemical shifts really. It's just something to keep in mind as the numbers may not be perfect. So number 5 is the number above each signal. Okay. And then I'll go ahead and talk about number 6, or write down what number 6 is. And it's something called degrees of unsaturation. Okay. Now this is a term and a formula that you have learned in OChem 1. But as a refresher, I am going to rewrite the formula here and you may have used a different formula. That's fine, whatever you're comfortable with. But this is the one that I use. So it's 2 times C, which is carbon, plus 2 plus nitrogens minus hydrogens minus X, which is all halogens. Um, parentheses. Actually, we don't need the parentheses. So all of this will be divided by 2. Okay. So again, carbon, C stands for carbon, N stands for nitrogen, H stands for hydrogens, X stands for halogens. Okay. And degrees of unsaturation, this is the first thing that you should always do whenever you get an NMR problem, because it gives you a lot of information. And this can be very valuable in identifying your structure. And this formula is used whenever they give you the chemical formula. For example, like C5H12, which is this right here. So you can use C5H12 to plug into degrees of unsaturation and get a specific number, okay? And I'll tell you what whatever number you get will mean, okay? So every single bond has a degree of unsaturation of 0. Every double bond in your structure has a degree of unsaturation of 1. Every triple bond has a degree of unsaturation of 2. Every ring also has a degree of unsaturation of 1. And a benzene ring, which has 3 double bonds, as well as a ring. So altogether, a benzene ring has 4 degrees of unsaturation. Okay? Some other ones, those are the main ones, but some other functional groups, NO2 actually has 1 degree of unsaturation because it has a double bond between one of the oxygens and a single bond between the other oxygen. Ketone has 1. Aldehyde has 1. Basically, any carbonyl is technically a double bond because it's a C double bonded O, so that obviously counts as 1. Of course, there's ester, amide, carboxylic acid. So there's ester. Carboxylic acid, and then amide. So all of these also have 1 degree of unsaturation. Okay? And like I said, depending on the chemical formula they give you, and once you take those atoms and plug it into this formula, and you get a set of, or you get a rather a big number. For example, let's say you get 6. that usually means that there is some type of benzene ring and and any of the following combinations. Technically, 6 could mean anything, really, but more often than not, they contain some type of benzene ring and some type of carbonyl. It's less common to have a triple bond or double bonds. Okay? All right. And so we just talked about number 6. So let's talk about number 5, the number above each signal. Okay? So to explain this, I will have to show the graph, which I haven't done as of yet. So here is a example graph, and this is our TMS, which means the most upfield structure has a value of 0. Okay. Now ignore the location ppm. Just understand what I'm trying to say by number above each signal. So let's say we have A, B, C. And actually before this, I have a problem that corresponds to this graph, which I will draw right next to it, and I'm also going to zoom in. Okay. So the problem will look like, sorry, structure looks like this. Now, of course, normally they wouldn't give you the structure right off the bat, but then again, it is multiple choice, so that may look different. All right, so this is our entire structure, and of course, the first thing you have to do is, well, they didn't give us the chemical formula, and we could technically get it and find degrees of unsaturation, but the whole point of finding degrees of unsaturation is to get the structure. So if we're already given the structure, we don't have to do any of that. We're working backwards. We're given a structure and we're trying to graph it. Normally, you are given the graph and you're trying to draw the structure. And again, because it's multiple choice and there's no free response, you will most likely be given the graph with a set of options for your structures as multiple choice. At least I believe. I'm not sure what the format looks like, but that's what I'm assuming because it's virtual. Okay, so I'm gonna skip ahead and tell you that there are, 3 unique signals, and while there is no symmetry, all of these have the same signal because there is rotational symmetry between this single bond and all 3 of these methyl groups. Okay, so that's C, this is A, and this is B. Okay. So 3 unique signals means I should see 3 set of peaks. Okay, and then let's do our multiplicity real quick. C is neighboring 0 hydrogens. So C's neighbor is 0 plus 1, which is a singlet. A is neighboring B. B contains 3 hydrogens, so 3 plus 1 is a quartet. So A's multiplicity is a quartet. B is neighboring A. A has 2, so 2 plus 1 equals 3. B's multiplicity is a triplet. Okay. And if you didn't understand that, or if I went too fast, go back a couple of minutes where I talked about multiplicity and how to find that. And if you didn't understand how I found A, B, and C, go back even further to to review what I talked about unique signals. All right, so now that we got our unique signals, we have our multiplicity, we can graph this. And like I said, we are going to ignore location for now, and we're just going to graph however, just using these two information. Okay? So under A is a quartet, so my signal should look like this, or my peaks should look like this. For B, I have a triplet, so my peak should look like this. For C, we found out it was a singlet because it was neighboring 0 carbons, and 0 plus 1 equals 1, which is a singlet. So it just looks like this. Okay? So 5, when we talk about the number above each signal, in a problem above A, the number of each signal above each signal quantifies how many hydrogens the A has. So A has 2 hydrogens, so I'm going to write 2 above it. B has 3 because it's a methyl group, not because it's a triplet. Don't get that confused. C has 3 methyl groups, so 3 times 3 hydrogens equals 9. So this should be 9, okay? Now normally, before I get ahead, so that's what you should see on your graph, and you will. So don't get this number mixed with your multiplicity, because let's review again. A, this is group A. Group A has 2 hydrogens right here, 1, 2, but it's neighboring 3 hydrogens because it's neighboring only a methyl group. Okay, that's why it's 3 plus 1, multiplicity is quartet, so we have 4 peaks right here. Okay? All right, and then of course so on. And then of course there's something called abundancy that we learned in mass spec. It's kind of similar in NMR. The higher the peak, well, not exactly most stable, but the higher number of signals we have, for example 9, this should technically be taller than the rest of these because it has more signals, more hydrogens. Okay. All right, so we're almost done before you completely understand NMR. We're going to take a look at 3 common patterns, 3 of the most common ones. Because chances are you will encounter one of these or more than one of these for a lot of your problems. Okay. So the first pattern belongs to ethyl. The second one belongs to isopropyl. And the third one belongs to tert-butyl or T-butyl. Okay. And I am going to draw what ethyl looks like. It has an R group and then 2 carbons. Isopropyl looks like R group and then 2 methyls at a center. And then tert-butyl has an R group and then 3 methyls. Oops. Okay. So if you notice, we're really just adding extra metals as we go on. This has 1 metal, this has 2, this has 3, okay? And before we graph it, let's find our unique signals, okay? So ethyl has A, or let's make the methyl A and this B. Isopropyl has A right here, as well as A right here, and then B. Terbutyl has 3 A's because they're all symmetrical. And there's no B because there's no hydrogen right here, okay? As well as, let's quickly do the multiplicity. A is neighboring B, B is neighboring A, so A should be a triplet. I'll just write a T. Actually, I'll just write the word B should be a quartet because it's neighboring a methyl group. So both A's are neighboring B, which is 1 hydrogen. So both of the A's have a doublet, but we only write 1. Now B is neighboring 2 A's, which contain 3 hydrogens each. So 6 plus 1, because of our formula, means it's 7. And anything 5 and above, we just denote it as multiplet. And then last, we have 3 A's neighboring 0 hydrogens. So 0 plus 1 equals a singlet for all 3. But we just denote it as single for 1 signal. All right, so now that we have all of that information, we are going to draw our graph. And again, like I said, we are working backwards. Normally you would see the other way around, where you're given the graph and you have to do everything I just did on your own. So there's our 3 lines. Okay. So for A, there is a triplet, and for B, there's a quartet. That's wrong. Okay. So once again, that's A. That's B. A right here. B right there. And then A again. Okay. So if you see a quartet right here and a triplet right here, that should signal you it's an ethyl. And don't forget the numbers above it. Above B, you should see the number 2, and above A, you should see the number 3. Okay. So if you see a 2 and a 3 paired with a quartet and a triplet, that should immediately signal that there is some type of ethyl group within your larger structure. Okay. This isn't the whole structure because there's more peaks probably, but this should automatically help you get your answer quicker. Now for isopropyl, A, because it has 6, it's going to have a larger or taller peak because its abundance is higher, and it should say 6. And for B, because it has 7, it should technically be a multiplet, but we're gonna draw all 7 peaks. So 1, 2, 3, 4, 5, 6, 7. Okay, and above it should represent how many numbers of hydrogens it has, and it has a single one. And then A has 9 hydrogen, so it should be even taller, but we're just gonna represent like that. And because it's a singlet, it just has one peak like that, and the 9 should go right there. Okay. And of course, there's no neighboring hydrogens. That's why you don't really see a B cycling signal. And yeah, so just like I said for ethyl, if your pattern looks anything like this, it's going to be an isopropyl. If your graph looks anything like this, you know to expect a terp-butyl within your whole structure. Okay. So we can kind of apply this to our example. We have a 9 here, and we don't really see a neighboring signal. That should tell us that there's a terp-butyl, which there is. And then there's also an ethyl, A and B. Granted, the letters are flipped, but the same concept applies because we see a 2 and a 3, and we see a quartet and a triplet. Okay? All right, so well, there you have it. That is pretty much most of the information, if not all of the information you need to solve any NMR problem. NMR is a very challenging concept that a lot of students struggle with. So if you're having trouble with any of these problems or understanding each of the 6 tools I mentioned, don't worry. Just keep practicing, keep listening to lectures, looking at your PowerPoints, reading the textbook, coming to these SSC additional resources, peer tutoring, PLTL, SI, come to each of those. And yeah, just keep practicing. Next week, we will actually go over NMR problems to help put everything that we learned this week so you are ready for your exam. And NMR and IR and mass spec is a semester-long concept that you have to revisit every time you come to a exam because it's very important to OChem 2 and how it's taught. Of course, each semester the curriculum might change, and depending on the professor, it might change. So, just be aware of that possibility. But for this unit, for sure, you can highly expect NMR, IR, and mass spec to be a good bulk of your exam. So make sure you truly understand all the tools. Make sure you understand the patterns. Make sure you understand that these spectroscopy is meant to be viewed as a puzzle, or rather, it's not meant to be. It helps to view as a puzzle to put everything together. All right, that should do it for next week. I will see you guys, or that should do it for this week. I will see you guys next week where we go over NMR problems and any other questions you guys have for the exam. All right, good luck.